Hello and welcome to a Chemistry Academy video. In this video we're going to be looking at National 5 level monitoring the rates of reactions. This will be useful for you if you're studying National 5 chemistry, obviously, but it would also be useful for you if you are studying higher chemistry and can't remember how you set up experiments to monitor the rate of reactions. So firstly, what is reaction rate? Most of the time you don't actually have to explain this to people when you're teaching it, however I'll just cover it just in case. It's essentially a calculation or a number that can indicate how quickly or slowly reactants are being converted into products. So when we're carrying out chemical reactions, we have chemicals that are known as reactants, so they're the things we start with, and they collide together in order to react and turn into our products, the things we are trying to make. In chemistry, we always lay out a reaction with the reactants listed on the left hand side, an arrow in between, and then any products listed on the right hand side. We don't use equal signs in chemistry. So you would have your reactants added on the left and products added on the right if you have more than one of them. So when it comes to, like I said, assigning a number to reaction rate, this is the equation you will use in National 5. You will find this at the front of the data booklet and the contents page, so you don't actually need to remember it, you just need to remember where to find it. This little triangle here is a Greek letter called delta, and it means change. So to calculate the average rate, we do the change in quantity divided by the change in time. This means that what we have to do is, while the reaction is running at regular time intervals, we have to measure a quantity of something. Now, most of the reactions you will see in National 5 produce a gas. So I've got an example reaction here. It's a very common one that you'll have probably done plenty of reaction rate experiments on, where we have marble chips, calcium carbonate, reacting with hydrochloric acid. So that produces calcium chloride, water, and then also the carbon dioxide gas. Now, if you're not sure if a reaction produces a gas or not, then you just look at the equation and look at the state symbols, and if you see something that's produced on the product side with a G, then that tells you that you are producing a gas. Anytime you are doing a reaction that produces a gas, in order to monitor the rate, you can either collect and measure the volume of that gas, or you can let the gas be released into the atmosphere and monitor mass lost from the reaction, because gases do also have mass. So if we let the gas leave the flask, then the mass of the flask should decrease. So we can always use the gas in order to monitor the rate. What we're going to look at now is what these experiments actually look like apparatus-wise, and then talk a bit more about the procedure of carrying out a successful experiment. First of all, we're going to look at how we set the experiment up if we are collecting the gas. So that was option 1 that I gave before. When you're collecting the gas, you have a few options. These are the most common two. So the one that you've most likely done in class is this one here, where you collect the gas over water. So what happens is you have this delivery tube that takes the gas produced in the reaction all the way into this measuring cylinder, which is filled with water. The gas that's produced then displaces that water, i.e. kicks it out of the measuring cylinder, and therefore you can read the volume of gas produced off of the scale on the measuring cylinder. You can't use a test tube for this because a test tube doesn't have a graduated scale, so there's no way of you knowing exactly how much gas is in the measuring cylinder, or in the test tube, sorry. So you need to have something with a graduated scale for this, so that's why we would have the measuring cylinder. Things to watch out for when you're drawing these diagrams that the SQA will pick you up on. Do not block off any tubes. So if you imagine you are a gas molecule, if you were to follow your drawing, would you actually be able to pass through all of the tubes, etc.? The water line is okay, it doesn't matter that that's cutting through, but like the end of the measuring cylinder, the end of the tube, it can't be cut off. You also need to make sure that the end of your delivery tube goes into the measuring cylinder a decent amount, because if it's down here at the edge, it could be seen that the gas could be lost to the edges. So you just need to make sure that it's clearly inside the measuring cylinder. One thing to note about this method though is that it won't work for any water soluble gases, because what will happen is your gas will just dissolve in the water rather than actually displacing the water. So it only works for gases that aren't very soluble in water. The other option you have, which is the easiest one to draw and works with any gas regardless of how soluble it is, etc., is using the gas syringe. So it's essentially a reaction, a conical flask with a side arm tube, as we would call it, and a syringe gets stuck onto there. Again, when you're drawing the syringe, you need to draw on the graduated scale. I should have said that about the measuring cylinder as well. When you're drawing this setup, you must draw a graduated scale on, because if there's no graduated scale shown, it means that you wouldn't actually be able to record the volume of gas produced. So these are your two options setup wise. For both of them, what you would do would just be to record the volume of gas produced at regular time intervals, so every 10 seconds, every 15 seconds, every 30 seconds, depending on your reaction. You do that until no more gas is produced, so that's when you keep getting the same number after a few repeated measurements. Okay, so that's the collecting gas. So we'll have a look at now what experimentally it looks like when we are monitoring the change in mass. This is the setup for the change in mass. I forgot to write it up here. Silly me. So this is the setup for the change in mass. So you have your reactants in a conical flask, or you wouldn't probably use a beaker because the neck's too wide. So ideally a conical flask with cotton wool in the neck of it. The cotton wool just prevents any liquid splashing out, because what we're wanting to leave the flask is just gases. So you have everything on the balance, and you're then just recording the mass of the reaction at regular time intervals. So again, every 10, 15, 30 seconds until no more mass is lost. So one thing to note here is that because the gas is released from the flask into the atmosphere, the mass is going to go down. Mass will be lost from the flask, so that 101 grams should go down to 100.08 or so on. So the mass should continuously decrease as the gas is released. One tip for this setup to make it more experimentally accurate as well is to weigh all of the reactants on the balance before you actually mix them together, so before you start the reaction. This just means that then any change in mass once the reaction starts must be due to products being produced. Okay, so sometimes you'll see questions in the exam asking why one setup's better than another. So in the case of this experiment, it's better to have all of the reactants and apparatus on the balance for the entire time, just so that then any change in mass is down to the products being produced only. That is a whistle-stop tour of how to monitor the rates of reactions that produce gases. These are my main key. These are what people normally forget. Don't forget them for the exam things. So most of the reactions you see in National 5 do produce a gas. Therefore, you can either collect it or release it in order to monitor the rate. Just remember, if you are releasing the gas from the flask, the mass will decrease as the gas is released. If you're collecting it, you must collect it in something with a graduated scale. When you're drawing your apparatus, don't block off any tubes that the gas needs to travel through, or leave any gaps where you're not wanting the gas to escape from. And then lastly, if you're answering an open-ended question on monitoring the rate of reaction, don't forget to mention about recording the volume of gas produced or the mass of the reaction at regular time intervals. That is a key part of the experimental procedure, is that the results are taken at regular time intervals. So that's just always an extra wee bit you can add into your open-ended questions, just to make it look like you've got a better knowledge of chemistry. If you're looking for help on calculating the rate of reaction or the effects of different factors on reaction rates, you can check those out in my other videos. you'll find in my National 5 playlist. If you found this helpful, please give it a like, don't forget to subscribe for future videos, and I'll see you soon.